Thanks for tuning into my video. I'm Marco Seiler. This talk is on contact process in an evolving random environment. This is based on joint work with Anja Sturm. We are both from University of Göttingen. Let us first talk about a general framework and the definition of this process. This process is defined on a graph G, which is connected, transitive, and has bound degrees. In this talk, we will restrict ourselves to set D, where this process can be defined on a more general graph. The process is split in two parts. This part C and this part B. B is the infection process, and B is the background process, which describes the evolving random environment. Let us first talk about B. The background B is assumed to be autonomous. This means it gets no feedback from the infection process. Furthermore, we assume that it is an attractive, translation invariant, and finite range spin system. This means we are in a Markovian setting. We call an edge E open at time t if it is contained in Bt, otherwise it is closed. Next, we come to the infection process C, which we will define via a graphical representation as the classical contact process. The graphical representation is a percolative structure of transmission errors and recovery symbols. Here we start with some initially infected sites, here 0 and 3, and the infection will travel along vertical lines and the transmission errors. It will stop at recovery symbols, which are denoted by crosses. Different as in the classical case, we will also include the background process by these white and gray areas. White areas denote open edges and gray areas denote closed edges. Therefore, transmission errors which fall in gray areas cannot be used. The transmission errors are placed with a rate lambda and the recovery symbols are placed with a rate r. This yields the following transitions. And site X gets infected at rate lambda multiplied with the number of infected neighbors which share an open edge at time t. And it recovers at rate r. Now we need to pose some further assumptions on the background process. For that, we define this permanently coupled region at time t, which we denote by psi t. An edge E, which is contained in the permanently coupled region, has already forgotten its initial state. This means from time t onwards, the state of E, so if it is open or closed, does not longer depend on the initial configuration of the background process. Our first assumption is that there exists a unique invariant law pi, such that the background B, regardless how we started it, in which configuration, it converges to pi as t converges to infinity. So the intuition is that this permanently coupled region will grow until it incorporates the whole edge set E. Therefore, assumption 2 guarantees that this happens fast enough. We assume that the probability that an edge E is not permanently coupled at time t decreases exponentially fast as t goes to infinity. And the last assumption is that B is reversible with respect to this invariant law pi. Next, let us give briefly some examples for the background process B. We will assume that on the edge set, we have defined a neighborhood structure, and the neighborhood of an edge E is denoted by NE. The first example is a dynamic percolation. B is here a Feller process with the following transition rates. An edge E is opened at rate alpha and is closed at rate beta. Here, no interaction happens between different edges. The second example is the ferromagnetic stochastic Ising model. As we see here happens interaction between different edges. We have an inverse temperature B. If we choose beta small enough, we can ensure that the first two assumptions are satisfied. Furthermore, the stochastic Ising model is a rather natural choice because by definition it is reversible, so the third assumption is satisfied. So next, let us come back to the contact process in a revolving random environment. One of the classical properties which one looks at is survival. Therefore, we define the survival probability of C by this theta. And then we can denote the critical infection rate for survival by lambda C. Here, lambda C is the smallest infection rate such that the survival probability is positive. Of course, this depends on R on the initial configuration C and B. Our first result is that actually this critical infection rate does only depend on R and not on the initial configuration. So as long as we start with finitely many infected sites, it does not matter which configuration CB we state, the infection rate or the critical infection rate is independent of it. The idea for the proof of this result is to compare the asymptotic expansion speed of the infection and the permanent decoupled region. Here on the left-hand side, we illustrated a contact process on Z with lambda chosen to be 2 and the recovery rate to be 0. So no recoveries are taking place. These black lines denote the left and rightmost particle. We see clearly that the infection area, which is between these two lines, grows linear with a speed of 2. So it takes until time 500 for every site between minus 1000 and 1000 to be infected. On the other hand, here on the right-hand side, we have the permanently coupled region if we choose B to be the dynamic percolation on Z. These black bars denote the time until one edge is permanently coupled. So we see that if we take 0 as a reference point, it only takes until time 4 or a bit more for every edge to be permanently coupled between minus 1000 and 1000. This is much, much faster than the expansion speed of the infection. So the idea is now that from some time onwards, the infection area is always contained in the permanently coupled region. So from this point onwards, the infection will not hit a not coupled edge anymore. So the initial state of the background process will at this time not matter anymore. Everything what happens before this time cannot affect the chance of survival since it only happens in a finite time region. Now we will talk about duality and the upper invariant law. In this case, there also exists an upper invariant law, which we denote by nu prime, such that if we start with every site infected and every edge open, and let t go to infinity, we converge to this upper invariant law. Similar as for the contact process, we can also construct for the contact process in a random environment a self-duality. Note that this only holds if the background process started stationary. The construction of the self-duality goes as follows. We reverse the time flow of the graphical representation and also reverse the errors. So we can use them from tip to toe. This is illustrated by these blue lines here. Note that it is important that the background process is reversible since we fix it and it needs to have the same distribution if we run it forward or backwards in time. Now we can define a critical rate for a non-trivial upper invariant law, as we did here, and we denoted it by lambda C prime. With the help of the self-duality, we can show that if the survival probability is bigger than 0, this happens only if the upper invariant law is not trivial and the other way around. But this implies already that the critical rate for survival and the critical rate for a non-trivial upper invariant law must agree. So we come to the end of this talk. We do have further results on continuity of the survival probability, complete convergence of the contact process in a random environment, and the critical behavior in the special case that we choose B to be the dynamic percolation. But since we don't have enough time to talk about them in detail, we will skip this here. Thank you for your attention. This is still work in progress, and it is expected to be available in arXiv soon.